Yes, I now mostly work at QOD here at the University of Warsaw, but I'll be presenting the work that I have been doing since around 2018 at NBI, which I still strongly cooperate with. And this work is quite different from what we do here as the central subject. Although not the only one, are the mechanical oscillators and how we try to put them in quantum states. So while quantum states may mean different things, because we can ask whether a ground state is a quantum state. Here we often understand that it requires so much of quantum engineering to put a mechanical object in its motional ground state that it is for us really reaching the quantum states. So some of the stuff here, maybe some of you have seen at quantum optics already, but I'll be giving also some new insights. And the plan is to first introduce where did the topic of quantum optomechanics came from, as it really came from some fundamental questions of how well can we measure the position of an object. And as it turns out, people have asked this question because they have been already considering the topic of gravitational wave detectors. And there you just really, really quickly hit the limit of a quantum limit of precision. And to understand what is this limit, one needs to put quite a bit of theory. And in more recent years, while the quantum limits in these detectors are clearly there, people have also been trying not really just to avoid them or somehow be as far from them as possible, but rather to make them the most pronounced. And thus, the field of quantum cavity mechanics was born, where we try to put mechanical oscillators that are as susceptible to quantum effects as possible into cavities, which make the light even more pronounced, etc., etc. And that has led to two experiments that I will be presenting, one of which is about reaching the ground state. And reaching the ground state, when are you in a ground state is really a subject of definition, but I will just present the path towards just reducing the residual occupation and then entangling the oscillator with something completely different. So let us first start with considering a mirror of which we reflect light, and we'll describe the mirror with the two operators x and p for its position and momentum, and the light that impinges on the mirror and then reflects back will be described by the quadrature operators. So now, if we just say that the mirror is a free mass, we may say that we may just use the very simple equations of motions for the operators, where F will be some force. And we present it as an operator since it will be a kind of stochastic force that depends on various things. In particular, it will be the sum of the thermal fluctuations, which will also actually contain the stochastic force that represents the ground state motion, but also the radiation pressure noise. So the force exerted by the photons that impinge on the mirrors. And we'll look into that in a moment, but before we'll just say that we can solve these equations in a Fourier transform manner, and just obtain that in general the spectrum or the Fourier transform of the position is some susceptibility to the force times this force. And that's motion. On the other hand, with light, as I said, we describe by a quadrature, and we will concentrate on a particular case where we have the space of light. So the coherent state alpha bar is some in classical optics, it will occupy just a point in a phase space, which represents the context number, that is the amplitude of a coherent state. And in quantum optics, we'll have some fluctuations around this point, and we in particular like to concentrate on a case where we have a big big coherent state and consider just some fluctuations. So x and y will be the fluctuations of the quadratures around some coherent state amplitude. And we like to say that since x plus iy will be expressed as alpha times e to i5 or like that, and since the real part is x and imaginary part is actually the phase, we like to say that x is the amplitude quadrature of light, or y is the phase quadrature of light. So as long as they are small, then clearly this is transverse, so the coherent state has these two quadratures. So we like to say that the phase is yes. So now let's say the following. Now we consider the interaction. So the phase of light will now change. So we needed this because now the phase of light will change as we move the mirror. So the phase of the reflected light will change as we move this mirror proportionally to the position of the mirror. And of course, there is the lambda as the wavelength of the light, but we really care about the scale here. On the other hand, the amplitude of light will be proportional to the position of the mirror. Therefore, we may calculate this radiation pressure force and obtain the following. So the radiation pressure force is really proportional to the number of photons that impinge on the mirror. So we expand it around this large coherent state and we obtain the following. We have a big force, alpha squared, a big classical force that just pushes the mirrors with all the photons, and we actually don't care about that. We may kind of always go into the frame of reference of this moving mirror, and usually it's actually a harmonic oscillator, so it will give us some spring countering this force, but we have these fluctuations. So now we see that the radiation pressure force on the mirror will be proportional to the amplitude quadrature of light. And that is a stochastic force. On the other hand, the phase quadrature of light will be the reflected one, will be pretty much the impinging one times the susceptibility to the force. And we plug in the thermal force and the radiation pressure force. And since this was proportional to light, we get alpha here once, while here the coherent state amplitude comes in twice. Therefore, when we want to actually estimate this phase of the mirror, this position of the mirror, given the phase of light, which we measure as per this equation, we need to divide by alpha, make a, let's say, a naive estimator, and we see the following. We have some factor that is inversely proportional to the light, the amount of light that we lose, and we have some factor that is proportional to the amount of light that we use. And also there is this part which is independent.
So Michał, but here you assume that your light is almost classical, or no? Or it can be arbitrary quantum here?
So I assume a strong coherent state.
And some quantum.
And some quantum fluctuations. So could this be a squeezed state here? Actually, yes. But I don't think it would work if so probably Gaussianity is actually needed for the moment here. So we see that it's not clear how to get the best precision because we don't know whether we should increase the alpha or decrease the alpha. So these factors, so this is the thermal noise. This is called the shot noise because this was present in the light originally. So the more light we use, the less shot noise we have. And this is called the back action noise. So this is something that which means that using too much light does something bad to the mirror, increases noise, therefore then we see that. Yes, so that leads to a trade-off. There is a fundamental trade-off for the optimum amount of light that we need to use. and and for that we need to make those two shock noise and back action noise contributions equal, and that has been termed the standard quantum limit. So we increase the probe strength, shock noise decreases, radiation pressure noise or back action noise increases. There is some constant factor, and the theory clearly says that you want to sit here to have the least noise. Because this is actually dependent on the susceptibility, and susceptibilities may be different for different oscillators. So you can see there's no susceptibility here, and there is a susceptibility here. Therefore, there is a different optimum probe strength for each frequency. And that's a frequency that you, let's say, you have some fluctuations of a mirror at some frequency. And you want to measure them, and it's a different optimum probe strength. Because if you look at the frequency, then for a given probe strength, we only touch the standard quantum limit in one point, in general. And that can be really observed experimentally by my colleagues a bit before me for one of our setups. But on the other hand, it's been considered long before. And one solution for that is using squeezed light. So then if we use squeezed light, we may change this curve. We, for example, may squeeze the phase quadrature, and then we'll have less shock noise. But actually, squeezing phase quadrature leads to anti-squeezing of amplitude quadrature, which will increase the radiation pressure noise. So what one really needs is some kind of squeezing that will be frequency dependent. But that's difficult, and I will offer an alternative solution. So looking for a moment into another practical.
I mean, unless you are not really at this SQL point, because you cannot pump the amplitude strong enough.
Yes,
it could be like
yes.
So you are limited by something.
So that's why squeezing is actually still useful.
Yes, even though you cannot.
Even though you do not really, you actually just roll this curve around. But here, squeezing has been used in LIGO. So this is really the noise of the gravitational wave detector, which limits the sensitivity to the displacement that they can sense. And we see this curve. We see also a rather peculiar behavior that it actually, so I've been showing before that usually this noise decreases with frequency. Here it has a dip, then starts increasing. This is because those mirrors, those are actually cavities. So here we go outside of the bandwidth of the cavity, therefore we actually just lose all the sensitivity. And when people use anti-squeezing, they usually just decrease the sensitivity. But with squeezing, they may actually increase the sensitivity, and that's the red curve. I think that's maybe a bit better visible in this. They got a bit better enhanced sensitivity in LIGO, but in Virgo they were able to also observe anti-squeezing. So yeah, there have been two parallel papers from both detectors at the same time. So a general solution would be okay, we want to use squeezing, but then let's just throw away this back action. And I will here show one of our original results that started also before me, and then we continued, is how to evade this back action. So the idea is, let's take two oscillators and measure them together. We'll have in the one shot noise, we'll have two independent thermal noises, and we'll have two correlated back action noises because they are driven by the same light. So if we now can somehow magically make sure that those susceptibilities are, when added together, they add up to 0, then we can cancel back action. And it turned out that such idea has been realized already for atoms. If you measure atoms in a similar manner, then it's enough to make spins of one atom point together with the magnetic field, and of some other group of atoms anti-parallel with the magnetic field. There have been some other ideas. So, for example, one can use quadrature rotation, so detect not phase but some rotated quadratures, and one can also make stroboscopic measurements, so completely different description as one needs a pulse description, but there are some methods. We'll concentrate on the first one, cancel the back action. So I've already written there that the idea is termed negative mass, because this object that will have this negative susceptibility, and that's actually maybe the more proper term, will just react very weirdly to photons pushing it. It will just go the other way. So the photons push it and it will go towards them. So there are no mirrors like that, but as I will show, the atoms can be made to do that. So we just really need, I want to say that this is no magic, we just want a negative susceptibility. So let's first talk about a little bit about the mechanical oscillator that we have. To be able to even think of this entanglement at this point without having a multi-billion-dollar project, one needs a nanomechanical oscillator, which will just have this quantum properties, or will be able to put it close to the ground state in an integrated setup. So the idea has been the following. People have been using for many years very tensioned membranes made of silicon nitride. So when one makes a membrane out of silicon nitride, it may be tensioned quite a lot, and then it becomes a very good mechanical oscillator. However, such oscillators still need to be attached to silicon frames, which will still make a lot of dissipation. The solution has been to take an idea from, let's say, even photonics, where often photonic crystals are used to create some kind of band structure to make a certain properties of light feasible. Here we use a so-called phononic crystal. So and I believe the idea has actually been around for many years, especially in silicon, but that's the first time it's been done on a very thin membrane. So the membrane just gets patterned into a periodic pattern. And the periodic pattern is such that the waves that we are interested in, which are at 1.5 megahertz, will experience with the speed. They are also periodic within the structure. So the structure acts as a Bragg mirror for the acoustic waves and reflects them back. So no waves from the outside may perturb the oscillator. On the other hand, we just displace some holes in the very middle of the membrane and create the so-called defect. And this defect is made such that it also oscillates at 1.5 megahertz. But now the waves at 1.5 megahertz from this defect cannot go out into the environment. So it's a double protection, but of course the fluctuation dissipation theorem says that it can't really be otherwise. But with that, what we really see is that we have a membrane, we put it in a cryostat, so it's cold, and then this silicon nitride becomes so tensioned that it just has a very high quality factor. So the quality factor is of the order of 1 billion, so it can make 1 billion coherent oscillations at 1.5 megahertz. One thing to remember, coherent oscillations, so that's like a classical oscillation. Now, the quantum coherence will depend on the number of phonons in the bath, and that's still 100,000. So in 4 Kelvin temperature. So the quantum coherence time the classical coherence time is 15 minutes. Quantum coherence time will be more like 1 millisecond. Yes, and then the membrane gets put into the cavity. So usually people consider a canonical optomechanical system where the oscillating the oscillator is one mirror on a spring, the other mirror is stationary. What is actually most often done is that the membrane is only partially reflective and it sits between two very high quality mirrors. So the thickness of the cavity P will be at least 10,000, and the membrane will reflect only a few percent of light. However, it will not really sense the number of photons impinging onto it, but it will actually sense the difference in the number of photons being in this subcavity and this subcavity. Nevertheless, that leads to the very standard Hamiltonian for an interaction that I don't really want to derive here, but we will be able to couple the quadratures of light in the cavity together with the x quadrature of the membrane in the cavity, exactly in the same way as I introduced at the very beginning, only that the membrane is actually a harmonic oscillator.
So what frequency of light is best to use here?
So actually, one needs to make sure that this silicon nitride will not absorb, because that will just heat it up. Therefore, anything above 800 nanometers will be fine. We use 850. People have been also using 1500 nanometers, and that often is even better. So very visible light would not be good, because this silicon nitride is not really transparent and visible. But on the other hand, it's also very thin, sometimes only 12 nanometers.
But apart from heating and absorption, no other effects are relevant, yes? On part of light.
No, I don't believe so. Unless you go very extreme, then it would just work. But as I said before, it gets put first into a cavity, so it must be quite cold to begin with, and the cavity is made out of those copper pieces. I will show some other designs later, and then put into the cryostat where we couple the windows. So one of the impressive features that we clearly see is already that we can see that we get this equation where we see the shock noise and the radiation pressure noise, and then when you also could detect the amplitude quadrature of light, that's a bit unusual, and it actually is unchanged. But with our cavity, the cavity will introduce some quadrature rotations. You may also want to introduce them on purpose, and what one may want to do is detect some combination of these two quadratures. So, as an example.
We have a question from Janek. Janek, maybe you can unmute yourself and ask Michał.
Okay, can you hear me? Sorry.
Yes.
So basically, I think I just wanted to make sure what Rafał asked, because this experiment should depend on the tuning, but is it so the tuning of the shine light to the frequency of the cavity? But I think you are. So I think you are in this linearized regime. So some kind of the interaction doesn't depend on the tuning. So you're saying, because you said it's good enough that
no. So it will highly depend on the tuning from the cavity. I mean, if you are very far detuned, then nothing happens. And if you are on resonance, and if you're a blue detuned, then it will just explode, right? It will parametrically.
Okay, so okay, then returning to Rafał's
question. What I said is that it doesn't depend on the general wavelength within the nanometer range, but of course the single megahertz range matters very much because it's a very narrow cavity.
Okay, thanks.
Yeah. So if we detect this rotated quadrature, then we will be able to observe the interference between the amplitude and the amplitude transduced via the back action noise. And then, if those two interfere, then they will yield a signal that is less than shot noise, because they will interfere destructively on one side of the resonance and only constructively on the other side of the resonance. So while this squeezing has for long been like a goal by itself, we actually usually use it to calibrate our system and see how coherent it is. So that's. And then, once we do that, then we understand the temperature of the system, we understand the tunings, and we may attempt to do the actual experiments. And here I would like to first introduce the experiment where we try to go deep into the ground state. So the understanding for this experiment requires a little bit more pictorial picture. Is that and it is the following. So we may, in this linearized regime, we may always consider that we can induce two types of interaction in the membrane. It can be light and Stokes scattering or anti-Stokes scattering. So if we park the laser to the blue side of the cavity resonance, it will strongly scatter photons into the cavity mode. And since this frequency is set to the mechanical frequency, those photons will be converted to phonons and excite the mechanical. So that's heating. And on the other hand, we have cooling. If we park to the red side of the cavity resonance and put those photons, then for this transfer, they must take away photons from the membrane. So that is cooling, and that is called sideband cooling. And we will try to make it as good as we can. So in this experiment, we really simply just did the sideband cooling. It's really just one laser, but we try to actually estimate what is the temperature that we are reaching. And for that, we park our laser here. And now, normally, the Stokes, room temperature, the Stokes and anti-Stokes sidebands are equal. But as you approach the ground state, and also that they will become less equal because there are just really no more photons to take away. And you also need to take into account the cavity profile, but if you are able to have filters that will count the photons in this sideband and the other sideband, then you will be able to get the temperature via some calibration. So here we have constructed a completely crazy filter. The filter is actually 4 filtering cavities, each of them around 30 kilohertz wide, which means that they have a finesse of 8,000 and are 60 centimeters long, so very long cavities. And 4 of them to have a sharp feature like that. So we have the spectrum, all the modes that the membrane oscillates with, and this is this band gap that is the region protected by the phononic crystal in frequency space. And we park our filters here so that out of everything, we are able to select only one mode, which is this high quality mode, the mode of the defect.
So the size of the resonance, of the cavity resonance is this green thing? No.
So the green thing is the combined resonance of these filtering cavities. So this is not the optomechanical cavity, but the cavities that just filter photons, so that we are able to observe only one side. And we may park these filters in terms of frequency, either here or here, and count one photons or the other ones. And then, as we do that, and we have some calibrations, then from the ratio of the sidebands, which plugs into the equation, we may estimate the temperature. And as we park on one of the sidebands or the other one, we also see an interesting feature. We see that the autocorrelation of the photons reaches the value of 2, which is a good indication that we are seeing photons from really the thermal state of the membrane, because the autocorrelation of 2 is a good signature of the thermality.
And what happens if you stop driving the cavity?
If
you just turn off?
If we would turn off light, then really the membrane would slowly heat up because it is being cooled by light, but also the photons would stop scattering very quickly. There would be no sidebands anymore because the sidebands are driven from the laser. And the light will decay much faster than the membrane because the cavity is still a megahertz wide, let's say. So after 1 microsecond, there will be no light anymore. We may now change the power of the laser and see that as we change the power, then as long as everything works well, then we approach the limit of sideband cooling, which is set by some parameters of the system, and we got to around 0.23 here. So it's just a picture of these filtering cavities. They've been actually quite more challenging in this experiment than the main cavity. So 0.23 doesn't really, so it's like 1/4 of the whole phonon there on average. So it's pretty close to the ground state, but not nearly as close as everybody would like to be. And to go even deeper, more noise needs to be reduced. So if we would go,
But the surrounding temperature is what?
is 4 Kelvin.
4 Kelvin, which means how many photons?
Phonons,
Phonons,
100,000.
100,000.
So if we would keep increasing the power here, then first of all we would hit this limit, and then it will actually keep increasing because more laser light contains more classical noise and also drives more classical noise from the mirrors. So I will briefly introduce those two problems. So to get this line below, one just needs a higher finesse cavity or a longer cavity. That's very easy. But then we hit the laser noise. So the laser noise is the noise, the classical noise of our titanium sapphire laser, and it reaches some value, but this value may be very easily connected with the occupation that one may get. And here we see that omega squared times the mean noise is actually like a frequency noise, so how much the laser jiggles, which means if the laser jiggles at this frequency, it really means that it has photons at the frequency offset of the mechanical frequency. So they will be just mapped into the membrane and increase occupation. So while this is the ultimate limit, and we didn't really know how to reduce all noise of the laser, so we constructed a setup that measures the noise of the laser using a 50-meter delay line of a fiber. And then we use this measurement of the laser noise, a very classical noise, to feed back on the light and to reduce noise. And while it's difficult to measure all the noise, we learned to measure the noise at our frequency of interest. So here actually 1.2 megahertz. And we reduced the noise around 10 times in its power, which turned out to be already enough. So that's one challenge that has been solved. And here is another challenge. It's very raw data of this band gap region. We see that it's not clean. So the membrane, this high quality membrane mode would be here where the red line is, but everywhere else we see some additional noise, and especially here. Turns out those are the modes of the other two mirrors that are in the cavity. And those, and to get rid of those, they really need to be engineered. So,
but this noise corresponds to this 4 Kelvin thermal.
Yes, that's already at 4 Kelvin. And those modes are very non-quantum. They're still very much classical because they cannot be cooled by light because they are very heavy. Like the photon force, it doesn't matter for them. So to solve them, we just need better mirrors and also more vibration isolation actually. So we have hanged our cavity on springs, kind of like in a gravitational wave interferometer already. And then of course it won't be cold. So there are also heat straps connecting the cold helium part to the cavity. And also one needs to reduce the radiation heating by gold coating the cavity. So those are some very recent developments. And the mirrors now need to be very small, which I will show in a moment, because small mirrors have very sparse spectrum of modes. And the sparse spectrum will just not fall into the membrane frequency. And that's just really engineering of these pieces of glass. But they still need to be clamped with very nicely engineered pieces of teflon. So before we had that, so we had all those modes of the mirrors that would just fall everywhere. And it's extremely difficult to fabricate a membrane that will be, for example, exactly here. And often it's still not good enough. But in a master thesis, one of our students have designed mirrors that have much sparser spectrum of modes. So now we have much broader regions where the membrane frequency can fall into. Okay, so we are there. We are not in the ground state yet because of this many challenges, but they really turned out to be a rather interesting engineering challenges. So now for the experiment that did not require such engineering, because as it turned out, when we are doing homodyne detection, then the ground state is often not required, because consider the following: if you are counting photons, then being in the ground state will really mean 0 photons scattered from the membrane. So the signal to noise ratio really is not so well defined. On the other hand, when one does homodyne detection, then being a bit above the ground state only increases the noise by some small percent, because that just goes slightly above shot noise. So this other experiment uses only homodyne detection and couples the membrane to the atoms. And the atoms are a hot gas in a vapor cell, but here we don't consider the mechanical properties, but only the spin properties. And the spin doesn't interact with the phase around it of light, but with the polarization via the Faraday effect. And this is already a very well studied effect, and I will not be getting deep into that, but we may couple this polarization quadratures of light to the spin quadratures, and if the spins are pumped into one direction, they will behave their Sx and Sy quadratures of the spin will look almost as the mechanical X and P quadratures of mechanics. Therefore, such spins may be considered like an oscillator. And now it is just easy to make it have a negative susceptibility by flipping the direction of the spin pumping versus the magnetic field. So now the entire setup for this experiment is the following. We send the light first into the spins, they interact with the polarization, then with some polarization optics, we map these polarization fluctuations to phase fluctuations. That is done via a simple interferometer, and this light goes into the membrane cavity, and then we detect it. So it's light that goes through both systems, collects, measures both of them, and then we detect it. So if the systems have different frequencies, so this is the membrane, and this is the spins, not much happens. And now we have the magnetic field, so we tune the Larmor frequency of the spins. So now the spin frequency is tunable. So we just bring it here. And we observe that if we put them together, actually in many spectral regions, we get less noise, because we do get this cancellation of back action.
Sorry, because these atoms are in the same cavity as the membrane, yes?
No, the atoms are completely separate. They're 2 meters away. And the light just probes first one and the other system. So that's really the advantage of light. That it
but they could be the same cavity, or it would?
Yes, there are some experiments like that, actually. Very interesting. They could be in the same cavity, and then one needs to think about how to, because they interact differently. They interact with polarization. So somehow those two need to be mapped. I want to slowly converge towards saying that when we measure the two systems like that, we are actually measuring the EPR combination of these two systems. So if our phase quadrature of light probes the two systems, and we go now into the rotating frame, then we will see that actually in if we demodulate our signal at 1.5 megahertz, we will get X and P. And if the systems have this opposite masses set, then they will actually measure X plus X and P minus P of the two systems, which are the EPR combinations. So to properly really extract all the information from this measurement, we use the so-called Wiener filter. And the Wiener filter is a simplified version of a Kalman filter that operates in a stationary regime. And it turns out that when to use it, one needs to know the noise of the system and how the system coordinates, such as X and P, map into light. And if we can construct such matrices, then we may construct our Wiener filter in the spectral domain and apply it to the signal. We could do it in the real time, but in this case, it was just fine to do it in the processed signals. So this Wiener filter nicely also talks to the description of stochastic master equations. But more importantly, I want to show the final result, where via this Wiener filter, we are able to estimate the trajectory of these two EPR variables. So this trajectory means the following. Those are the estimates of these EPR combinations. We start with no estimate. We know nothing about them, and except that the mean values over the entire lifetime of the system are 0. So as we start measuring, we know nothing. But then the Wiener filter tells us that we learn about the system and we estimate those positions better, and our variance drops down. So as we get more, accumulate more signal, our variance falls down and reaches some steady state value. And this steady state value is actually below what would be considered a ground state of each of one or the other oscillators. And this is allowed because those combinations, the EPR combinations, they may be called X and P, but they just do not satisfy the Heisenberg uncertainty. Just so that was the original Einstein-Podolsky-Rosen paradox, that those two variables seem like X and P, but they actually just commute. So there is no limit. And if one can make a system like that, that actually means that the system is entangled. So very much long time after Einstein, Podolsky, and Rosen, it's been proven that actually, yes, but if you go down below this, what would be an analog of this Heisenberg uncertainty, that means that you have entangled the system with of which you compose those two variables. And our variance reached around 80% of this ground state variance.
Usually now you say something stronger, that the system is steerable.
Right. So steering is yes. So actually, to prove steering, that would require a little bit more, because then you need to consider some conditional variances, and they were a bit higher from what I remember. So we didn't want to claim steering yet, because and there are so many. So I think that what we have here is that we would have both one-way steerings each way, but actually we wouldn't have the two-way steering.
Okay.
So those are a bit different concepts. The just falling below some EPR variance is, let's just say, more traditional, but this spectrum of being able to violate some inequalities has really evolved in recent years, indeed. So we see that actually our filter works even if the systems are not exactly tuned with each other, and this interference is not perfect. So even if this hybrid system has noise a bit higher than the noise of the mechanics itself, in this case, it turns out that it's still lower than both systems, and they still interfere, and our Wiener filter allows us to go below the ground state variance. So final important comment is that I want to stress that this is this entanglement here is really done by a measurement. So we learn to measure those two variables, and and therefore, by making the measurement of this entangled EPR variables, we project the system onto an entangled state. So really, if one would consider, maybe philosophically, that if we didn't measure, then they wouldn't be entangled. There is no transfer, there is no interaction between the two systems. There is just a joint measurement. Okay, and just showing the final challenge. This is really what one has to just go around to get that. Filter out all the Vanguard noises, filter out other high quality modes of the membrane, filter out mirror noise, electronic noise. Well, shot noise is always there, so that's normal. And if we get the full Wiener filter, then we get really the best result. So the experiment that some of my colleagues are now working on actually is a slight modification where you don't entangle, you actually make this joint measurement via light and via entangled light. So you generate two correlated beams, one of which goes to atoms and the other goes to a mechanical system. And now those two frequencies of light can be much different because here they generate 852 nanometer that goes into the cesium cell, and here they go 1064, which is just what is used in a gravitational wave interferometer. So entanglement of light allows a joint measurement of the two systems. And let's just say that that is still a bit away from being complete, but a very interesting theory nevertheless. So thank you. Yeah.
Okay, thank you very much. So now we have time for questions. So both here and both from the online participants. I see something on the chat. Yes. So Janek has a lot of questions, but he wants to wait. Maybe somebody else wants to ask first. Okay, so maybe Janek, maybe you ask one question.
Okay, I'll just.
Yeah, go on.
Well, so one question is, Michał really went fast over it, but I understand in the system you have this bad cavity limit and sideband resolve limit, which is the width of this Lorentzian. So for this experiment to work, I understand this width of the Lorentzian has to be narrow. And my question is this natural in these experiments? Do you need to work hard to achieve this? Or would this experiment also make sense when you don't have this? Thank you.
Yeah, so in the sideband pooling experiment, indeed, to go deep into the ground state, you need the sideband resolve limits, so a good cavity, I would say, right? That means that the cavity needs to be narrower in the line width than the mechanical frequency. On the other hand, for the other experiment, actually, we've been in this weird regime where they are two almost equal. So it's neither of the limits. And what are the trade-offs? The trade-offs are the following. So the better the cavity, the lower you can go to the ground state, but actually less of the perfect interaction you get. Because if you are in the sideband result limit, you may only do the cooling or the heating. But often what you want to do is to experience this perfect Hamiltonian, which is often called the quantum non-demolition measurement, which just couples. Let me show that. Yes, here. No, but I didn't really switch the slide. Sorry. Yes. So the perfect Hamiltonian that often is wanted is this one, but that one actually only so now that one only really happens in the effectively in this sideband unresolved limit. So when the cavity is much broader than the mechanical frequency. So there are some trade-offs, and some experiments want one, and some want to be somewhere in the middle. It's something that when we plan to have some result, we usually make a calculation, almost pretty much an exact one, to see what will be practically the optimal one here. How do we trade off with given quite many experimental parameters?
How much? I mean, how much the theory is really precise regarding your experimental results and how much you just have to, add effects that you see in experiments.
So I would say I was working with that. I was rather amazed how the theory works well here compared to atoms, let's say, where there are many effects that we need to put in somehow. The mechanics really, given that there are some engineering challenges, like sometimes, okay, there is for example, everything is a bit hotter than expected, but those are in a way well understood classical effects. On the other hand, all the quantum part is extremely very modelable, I would say, like the theory performs really quite well compared to some other systems. So a lot can be predicted. And when one designs an experiment, there are some bounds, but if one can then put them in Mathematica and actually get. And it does need to be a quantum theory. Like we do always consider all the quantum noises, and but nevertheless, for here it is usually the linear theory. One other place where another theory comes into place is this, and the design of these membranes. And theory is not that precise here, but obviously this is a simulation. So it is done in software called Conditional, which is a very powerful solver of finite element solver of many differential equations for its material. The process is rather complicated, and then the results are very precise. But then, of course, when the fabrication comes, there will be some variations.
So, any other questions? I don't see questions among the audience here. So, Janek, you have another question?
Yes, it's very simple. How do you convert the polarization into the quadrature of amplitude? Michał said it's easy, and he went very good.
Lovely. Yes, I didn't say. I agree. So imagine the following. So we send in a strong beam here, and that is linearly polarized. And now the atoms will rotate this polarization a tiny bit. So now, when you come back, then this drive light is actually made such that it is rejected by this polarizer, but only those fluctuations come through. And those fluctuations come through here, but then we use an additional beam that was just sent here. And this beam is also such that most of it is rejected, but a tiny bit comes in here. So what happens is that only those fluctuations interfere with this beam in this interferometer. So after this polarizer, we have an interference of the fluctuations with a classical beam. And of course, now depending whether those fluctuations are in phase or out of phase, they map into the phase or amplitude quadrature of light that is here. So what we really do more theoretically is we have this coherent state. We put the two atoms, it gets rotated in the polarization space. We reject the coherent part. We only are left with the varying, like light in the other polarizations, and we just put the coherent state in the same polarization, and then it interferes. So the phase matters here. Interferometer needs to be locked. This is the phase, really, of that translates how polarization is translated to fluctuate light quadratures.
Okay, so I don't see any other questions. So I think that we can thank Michał again.
Thank you.